especially around Graviton, Spot, and most of these customers, or the customers that I talk to, are using Kubernetes, right? So most of my time has been around Kubernetes autoscaling, specifically around Karpenter, KEDA as well. I wrote a book about the topic. It's called Kubernetes autoscaling, if you would like to give it a look later. So for today, it's gonna be about how you can start running small language models on Kubernetes in a more efficient way. So the reason of the topic today is that because we see a lot of people using LLMs, chatbots, and things like that. So I wanted to bring to your attention what else you can do about it, how you can optimize it, how you can run this more efficiently, right? So when I say a small language model, what I say is models that are between 1 to 10 billion parameters. And specifically talking generative AI models where you can get this amount of parameters, but in classical machine learning models you can get even lower, right? So those models who run below, who has less than these parameters, are gonna be suitable for into the category of small language models. So let's put you in context. What happens when you paste something into your favorite chatbot and ask something like this? This is kind of like a real question. What does mean values do? Is my config correct? You can paste it and that's it, right? Without any more context. And what is gonna happen is that the chatbot, this is a real test that I did a while ago, like 3 weeks or a month ago. It says mean values is not a standard field in Karpenter's requirement. And it starts to elaborate the answer, so it looks like it's pretty confident, it's well formatted, but it's wrong. Mean values is actually one of the latest features that was released on Karpenter, that it basically helps you to guarantee the number of instance types, in this case for the bean packing algorithm that Karpenter uses for schedule the simulation, right? So in this case, it is actually it's a field that exists, and that the LLMs start to hallucinate. Okay, I guess that we all seen this point, we all seen this, and my point is not to, hey, LLMs are bad, or perhaps the prompt was wrong, you need to start working on prompting and things like that. So my focus is gonna be take a different angle this time, and what I'm gonna basically talk about is that specialization beats sizes. And it's not me who's been telling that. I'm referencing a Salesforce paper where they actually fine-tune a small model that they were able to see that better results with a bigger model. Again, when you fine-tune a model, you make it specialize into something, you might get better results at it. So I think this is okay. And the other topic here, or the other phrase that I like to bring when I talk about this, is that AWS CEO says the CPU story is as big as a GPU story in the agentic AI story. Let me tell you why. So it's not only just these chatbots as examples. There are a lot of companies. I've been working with companies that have been running small language models as well, and in conjunction with the large language model as well. This is not a topic about, hey, LLMs are bad, GPUs are bad. It's actually trying to choosing the right tool for the right problem. So you can see here, if we put it into a perspective, into the whole API pipeline, we have different elements in it. In the center, you can see the LLM inference, where everyone has been talking about it. But if you look a little bit wider and you look for it, you're going to see here that there are other tasks that are already perfect scenarios for running on CPUs. Embeddings, classification, reranking, input validation, orchestration, and we are going to show you a demo for it. And last bit for this in my introduction, what I wanted to say is that, hey, SLMs already, you don't need to think about complex things like the device plugging scenarios, talking about GPUs, if you have to slice it or not. I've seen companies that actually want to use GPUs and they start to struggle with time slicing the GPU so that the small model can take advantage of that. So why don't you just give it a try to CPUs as well? We already have the primitives there. I don't think it's something new here that I'm telling. Kubernetes was not built from the ground up to run GPU workloads. It's been complicated. We're trying to work on that, and we're progressing, but we're not there yet, right? So why don't we give it a chance to this? So let me show you and put it a perspective into architecture and trying to inspire you, so to speak, right? So it's not gonna be what I'm gonna show you here is like it's not official pattern. It's not something that I'm gonna tell you, hey, this is exact formula that you need to follow. It's just an example of what I've seen companies doing and where all of these topics have been into it, right? So a few use cases, a real-time inference, depending on your SLAs. If your SLAs are really not really big, but are generous, instead of having to require like milliseconds, you can be more flexible and perhaps use a few seconds. The reality is that if you run generative models on CPUs, the latency is going to be higher. I'm not going to lie to you. It's a fact. And the throughput is going to be lower. So what else can you do in here? So I've seen customers running batch inference, for example. I had a customer that was running on GPUs and realized that, hey, my customers don't need that my response is quick or really fast. So I'm gonna give it a try to batch inference, and the results are gonna come later, and that's it. They were able to cut cost as well. Agentic AI subtasks as well, like for example, triage, running tools, or running in a sandbox environment. That's a perfect scenario for running on CPUs as well. And classical models like embeddings, reranking, scoring. And I'm gonna show you in a moment different of these use cases, how they tie to an architecture. This is basically what I'm gonna show you in the demo today. It's kind of like an evolution of what I show you at the beginning. We're gonna show you, it's gonna be a chatbot. Yeah, I'm sorry, but it's gonna be a different chatbot that is gonna be running on CPUs, and it's gonna be able to do some things in autopilot if you allow it. Right, so for example, it's gonna use you're gonna receive a query, and there's gonna be a small model fine-tuned for that task, where it's gonna say, hey, this is relevant to the domain that my chatbot or that my agent is able to resolve, or it's not, and it's gonna reject it, and kind of like we're protecting the final call to an LLM. If we wouldn't have this, all these calls might go directly to LLM, consuming tokens, consuming GPU capacity as well, and you might not actually need to do that from the very beginning. Another pattern that I've seen with customers is that they have an SLA of a latency that, as I was saying before, in this case could be 2 minutes, and instead of running GPUs or the LLM for all the tasks that they have, they said that, hey, why don't we parallelize certain tasks like classifying, filtering, preparing the output in parallel to the LLM, so that we can, at the end, when the LLM finishes what it was doing, we can merge the results, and that's going to be the answer or the task that it needs to be done. So they were able to take advantage, because from the philosophy that this company follows is that GPUs are great, but only if you can take 400% utilization. And I would say that 100% utilization in the GPU might tell you different things. So it might tell you that, hey, it's processing a very complex query, but it's not that busy. As soon as that finishes, boom, it's free. So it's actually a bad metric, and it depends on how well you are working on your application, how well you're using the GPUs. You might take advantage of that. Reality is that nobody, perhaps a few people, is able to do that. Therefore, companies like this are trying to decouple that into doing things like this. But it's not going to be only about trusting everything, right? So I know that the SLMs are not going to be as capable of, for example, as an LLM. So we need to kind of like use an LLM as a judge as well, depending on the confidence that the SLM could provide. So if you want to make sure that you have an accurate answer here, let me thought that I closed everything, all the notifications. Sorry. Instead of trusting the SLM confidently or blindly, we can have an LLM as well to validate the fact in here. So what I'm gonna show you here is basically how I built the demo and the project that I built to to make this a reality as well. So it's a project. It's basically a simple reference architecture that is called SLMify, where would you just simply with a YAML file you specify the domain expertise of your models. You specify where your data source is. In this case, for example, it was basically hundreds of emails, raw data like that. And the tool, what it does is simply fine-tune that model, a base model that you have from Hugging Face, and it trains it, and then it deploys it so that it's going to be a report. It's going to tell you a first glimpse of how the model will look like, right? So if it's not going to be something that you can fine-tune, it's going to help you to make it diversifiable, so to speak, that you can run it in multiple instance types in a quantization way as well, so that you can take advantage of the throughput of a CPU. All right, so this project, what it does, is basically helping on different models or different tasks. One is going to be generative models as well, but classical models as well, like classification, scoring, and embedding. Two build paths. If you are not going to be fine-tuning, as I said before, it's going to just convert into a compressible format, GGUF, and then you can quantize it, which is basically what I did, and it's going to serve it on Kubernetes, simply so that you can have something already running there you can start testing. If not, it's going to do kind of like following the same approach, but it's going to do a fine-tuning. In this example, what I'm doing is taking all the raw data and using an LLM to create synthetic data, kind of like Q&A questions, and it's going to use that data, and it's going to fine-tune it, and then it's going to follow the same process from the top here on the green. So this is basically the example. One of the examples that I use. It's for no surprise to no one, what I built is a Kubernetes autoscaling agent, expert on KEDA and Karpenter as well. And in this case, I'm just fine-tuning the first model, the triage model, to say, hey, if it's a question related to these topics, let it in. If not, block it. And I'm basically teaching the model how to react to this. And as I said before, it's basically 76 emails, and I created more than 2,000 synthetic pairs with an LLM as well, so that basically I'm generating more examples of what could be look like. Data here is very important, so you need to make sure that you validate what these synthetic pairs is being generated. So throughout the process, what I did is, hey, why, if I can fine-tune a model, does it make sense to fine-tune all the models possibles that are in my AI pipeline? Fun fact is that none of them actually saw a value or a gain. For example, I had another model, a classical model, as I was saying before, a retriever, because I'm implementing a RAG system here as well, and that actually turned out to work very well. When I get the documents as well in the RAG, I basically re-rank them, and if I fine-tune that basically didn't do any help. And the generative, actually the one that is doing kind of like the brain of the agent, fine-tuning that, it gave me no gains at this point in time, or for my use case, right? Because already RAG was given the precise context that it needed, and the model was already capable of answering that question. It was an 8 billion model, perfectly running on a CPU. I'm not saying that you cannot run it on a GPU. It's basically just to show you the fact that you can run it on CPUs. All right, so what it costs? As you can imagine, you don't need to, if it's going to be classical models, you won't need to use GPUs. Instead, unless you are going to be fine-tuning a bigger model, then of course the maths are gonna pay off by running a GPUs. But for my cases, I just needed to fine-tune two small models, classical models, and it was not needed to use GPUs. The good thing is that here I have a constant or a flat cost per replica, so I know how much will it cost. It's not going to be driven by how many tokens. If it's going to be self-managed running on Kubernetes, I have kind of like that freedom, so to speak, because I already pay for it, or it's going to be already running there, and it's basically going to behave like a web app, so to speak. So let me show you a few things. And like I said before, is I'm not trying to tell you that CPUs are gonna be kind of like the new trend. It's basically you need to know where does that fit, and I hope that with the next slides, this is gonna be even more clear. So I guess that we need to remind you, we need to remember a few things like the two phases of what happens for generative AI models. There's going to be the pre-fill phase where all the tokens are processed and from the prompt, and it's going to be very CPU intensive. And it's going to do the work on all the math calculations or the matrix calculations that we already know. When it starts to provide the answer, it's going to decode it, and that's going to be very memory bandwidth. And this is at some point the limitation that we have here on GPUs. That's going to be completely different. The way it works, the architecture it works, that's what they are shining for it. But for CPUs, we need to understand that limitation. So what are we looking at it? This is basically just on a test that I did. It's not, do not follow this blindly. It's not kind of like a benchmark study that I did. It's just basically for the use case that I built. Of course, the more tokens that I was putting in, or the more tokens that I needed to process, the more time it took. Typically, what I've been doing is that if it's a simple answer, I might not need to use too much tokens. But if it's a complicated answer where the agent will need to collect documents from the vector database, the tokens will increase. Therefore, the latency will increase as well. And I'm talking here only on the time to first token, because what you can do once you get the time to first token is start to decode the answer so that it looks like that it's gonna start already, or that he already got the answer, when in reality it's gonna start to stream the answer as well. So yes, the fact is that you can run generative AI models on GPUs. Just know that the latency and the throughput is gonna be perhaps the bigger bottleneck for you. But I do have customers that for their SLAs, this is actually a good alternative. So coming back to the part that I was saying before, that specialization bit sizes, it's going to be running fast on CPUs. If you run things like for classification, embeddings, yes, you can send that to an LLM, but it will take more time, and it will take tokens that you might not need. And of course, it depends on, once you have your application up and running, you might start to think about how to optimize it. Well, this might be a way and a good option as well. So let me show you basically on the first part, on the latest part of how to scale it, because I think that this is important as well, and how when you're running them on Kubernetes and more efficiently. So the first part is, I guess that this is not any news for running LLMs. It's not going to be any news for running SLMs as well. You don't need to scale on the typical metrics of CPU and memory, even though they can run on CPUs. It might not gonna be a good idea. CPU utilization is basically a lagger metric. It's already telling you when it's already too late, so to speak. llama.cpp, BLLM, all of those inference runtimes already provide you with metrics like, for example, queue depth. When a request is being queued, it might be a good time for start to scaling out. I have customers that actually fight into, hey, I don't want any request to be queued up, and they use KEDA as well. You could use KEDA as well for scaling that up. And what KEDA has is something that is called scaling modifiers, which is basically a very good feature that I don't hear people talking very often, where you can specify formulas for different triggers so that you can speed up different metric to scale out, and you can give even more weight to different metrics. So in conjunction with this, we basically using Karpenter as well. It's a no provisioner for Kubernetes, and what it does, you can see here that in less than 50 seconds, if it's this type of project, you can get the node up and running in 24 seconds. The image, depending on how big it will be, you can get it into a few seconds as well. And what it pays off is basically the warm-up. the subsequent requests that you're gonna have here are gonna pay off, and you're gonna the latency that you're gonna get, it's gonna be better if you warm up correctly. All right, so let me show you how it looks like. What I built is basically this. I have different models. The ones that you see in yellow amber are the ones that I fine-tune. The other ones are stock, and the purple one is gonna be basically running an LLM. And what I actually do, because I want some tasks to be as automated as possible. There's a CPU where there's a pod that is running on CPU for sandboxing all and give it a try to the queries that it's gonna run, so that I can basically scope the actions that the agent is gonna perform. The agent that I'm going to show you, it's a read-only format as well. You can approve a few changes that it's going to run, and it's going to be basically as well able to run in autopilot. And this is basically just what I said to you before, right? It's basically saved by default, and I'm running all of this into a constrained environment. So let me show you this very quickly. This is the project, by the way, that I showed you before. I include here a few different tasks, or the different tasks that the project supports and how you can use it. And I'm very clear about saying when to use it and why to use it as well. You can basically define it something like I was saying before over here, as I was showing you in the deck. And if you're, because I know that now who's not going to be using Claude or KEDA or something like that, I already provide you with the skill, so it's gonna ask you and it's gonna guide you on how to set up the project, and it's gonna actually interview you for your project to find out what are the parts of your pipeline that could be really benefit for this type of tasks. I include all the references here that I used. And I actually go into a series of deep dives where I explain each stage and the tools that I use, why I use certain tools, and basically the logic behind it, right? When you run a fine-tuned model, of course, what I told you is that the result is going to be a pod, or that it's going to be running on Kubernetes, but it's also going to provide you with a report like this. So it's gonna give you the accuracy, how many classes it was able to identify, the response time, and a few other training metrics that are useful here. The learning curve that you can see here that it's dropping, the data distribution, how well was distributed with the sample data that you provided, and just a glimpse of or a preview of how much will it cost to run that same workload based on the results that it got, right? So you can see here that at some point it's gonna pay off, and you're gonna see the benefit of running this. All right, so let me show you here. This is basically the agent running. Let me refresh it here. Let's see if it's not broken. And this is basically the demo or the workload running live. I'm gonna come back to here simply because I want to show you something here. So if I do something like, hey, the same question that I asked before, you can see here that it's gonna start doing something here, and I told you it's not gonna be faster as an LLM or as a chatbot, but you can see here all the different phases that basically started to stream the answer. It's gonna be more evident in a more complex or a more extended question, but I wanted to highlight here the latency. I want to highlight here the latency that you can get from the different models. CPU as well, 23 milliseconds. The router, I don't know what's going on. Okay, maybe I need to be more gentle. All right, so in this case, you can see here that it's following basically all the architecture that I was telling you before. And the time to first token, it was in less than a second as well. But look at this. I don't trust the answer, so I called an LLM to see if it's gonna basically the answer was accurate, right? You can see here all the process that it follow. Now let's try with a more complicated answer or a fresh question. Sorry. And again, this is gonna go and look for documents that are relevant for the question in VectorDB. What I did is that I filled the vector or the document DB with docs from KEDA, Karpenter, all the best practices. And you can see here that in this time it's basically taking more time to react, because it's basically gonna be about the first token. You don't see anything here streaming yet. It's gonna take around 40 to 30 seconds more or less to get the answer, because it already got the documents that it needed, the context that it needed. I'm looking for 10 documents, for example, well, 38 candidates, and it retrieved only the top 5. 45 seconds it took to get the first token. But look at this, it's still streaming the answer. So even though I'm already seeing here this, it's gonna be streaming the answer. And what is gonna be interesting here is that in this case, it's gonna go and say, hey, I need to go and run some tooling into the cluster. So I'm gonna investigate, and I'm gonna again run the same pipeline again, get more context to it, and refine the answer, because that answer that I provided I was not happy with it. I'm gonna you're gonna see here that again it's gonna give it a try, but still it's not gonna be enough for the answer, so it's gonna then fall back to the LLM, and it's gonna reply even faster that way. I have a few examples here as well. For example, fixing the cluster that I have for some pending pods, it can actually not see that it's not working, and it's gonna apply the fix. All right, I'm gonna leave it here. Well, it actually replied in 43 seconds, and you can see here that it's still streaming the answer. Yep, it's streaming the answer. And then when it finishes, I think that this is the case that it didn't like the answer, so it fall back to the LLM. You can see now the difference when you get from the LLM the response. Yet here there was something that it was not able to get, simply because I was actually asking something within my cluster that it didn't exist, right? So it was kind of like I did this on purpose. I didn't deploy something in my cluster, so that you can see here all the workflow of all the different paths. That again is not something I didn't want to show you, that hey, you need to use CPUs only from now on, because it's capable of doing it. It's just simply the fact that you can start building things like this. So let me close that up here. And basically go with concluding with what I show you, right? So what this means for you, if you already have parts of your pipeline that are already routing, there are already validating, classifying, guarding, running tooling. I see more and more the trend of customers asking for agent sandboxing. That's what I wanted to show you, that the capability of doing that, and reinforcement learning as well, that those are some tasks that are suitable for running on CPUs as well. So I just wanted to leave you with that inspiration as well, so you can think about it and consider it. Simply just to close up, when to use CPUs? Again, classical model CPU to classify, embedding, re-rankings, as I was showing you before. Don't trust all the information that it's gonna be getting there. You can also have your LLM to verify that. But the trick here is that you're not gonna send the full context. You're gonna decide what to send. So therefore, your optimization on how many tokens you send to the LLM is gonna be optimized as well. And of course, GPUs, if your SLAs are more tight and you need to run real-time inference in less than 5 seconds, 3 seconds, and not have to wait for 30 seconds or 40 seconds, as I show you as well, right? And the throughput is going to be even bigger. So that's it. Start here. Start to identify where you can optimize your AI pipeline. Fine-tune it if you think it's going to be something that is gonna help, you can test it with that project with kind of like that same approach or pattern or mindset that I showed you before, and deploy it. It was, as I was saying before, it was not a replacement of GPUs or LLMs. It was just a complement and to show you where each tool was going to be solving which problem. So that was it. Thank you very much, and thanks for having me again.